Have you ever tried to write a scheduling application by hand, or a seating planner, or a puzzle solver? So you start with this clean little loop, and then the special edge cases start to pile up. This person can't work that day. No one can work 2 days in a row. Keep it fair. And pretty soon you've got nested loops, backtracking, and a pile of if statements that you just do not trust. But here's the thing, right? For a whole class of problems like this, you don't have to write the search function at all. Instead of telling the computer how to find the right answer, you just describe what the correct answer looks like, the rules, and a tool called an SMT solver can find one for you. Or, and this is the magic part, it tells you with a mathematical proof that no answer exists. So in the next few minutes I'm going to show you exactly what an SMT solver is, and we'll build a real one, an on-call rota for a dev team, from scratch. So let's go. Right, let's get the jargon out of the way because it's scarier than it sounds. We'll start with satisfiability. Now imagine a wall of light switches and a list of conditions like switch A and switch B can't both be on. Satisfiability just asks, is there any combination of on and off that makes all the conditions true at once? The classic tool for that is a SAT solver. SAT as in satisfiability. It's brilliant, but it only speaks one language, true and false. The trouble is, we all know that real problems aren't just true and false. They've got numbers. This shift count has to be at least 1. This day can't equal that day. So we want something that understands arithmetic too. That's SMT, or satisfiability modulo theories. Now don't let the modulo theories throw you. It just means satisfiability plus some built-in knowledge of extra topics, like whole numbers and arithmetic. So you can write x plus y is greater than 10, or x is not equal to y. And the solver actually understands what plus and greater than and not equal mean. It's a SAT solver with a maths brain bolted onto the side of it. And here's the mindset shift that makes it powerful. Normally as programmers we write how, the step-by-step algorithm. With a solver you write the what, the rules, and you hand them to an incredibly optimized search engine that's the product of decades of research. You describe the problem and it does the searching. It comes back with one of two answers. SAT, yes, here's a concrete solution, or UNSAT, no solution exists. And the second answer isn't the program giving up, it's a proof that your rules can't all be satisfied at once. Now hold on to that. It's going to be the best part of the demo. Now the solver we're going to use today is Z3, which is free, open source, and has a really nice Python interface. So let's giddy up and start building something. Okay, right, installing this is just one line, pip install Z3 solver. What you'll notice is the package name is Z3 solver, but in the code itself we're just going to call it Z3. Then we're going to import a handful of pieces. A solver, and that's the engine that we're going to feed the rules into. Int, which is what's going to help us handle whole number variables, and a few little helpers to help us along the way. Or if and sum. And we'll meet those as we need them as we go through the rest of the demo. That's it. In the next step, we're going to start to describe our problem. Okay, here's the situation. We've got 4 engineers, Alice, Bob, Carol and Dan, and we need one of them on call each day for a week. So I'll give each engineer a number, 0 through to 3, and each day a number 2, just so that the solver can do the arithmetic with them. These constants at the top there are only to keep the code nice and readable. Now the key modelling decision, and this is where the solver thinking gets a little bit different. What I'm going to do is make one variable per day, called on-call, and each one is an int, or a whole number that the solver gets to choose. The value it picks for, say, Wednesday is which engineer is on call that Wednesday. And what you'll notice is we get something for free. Because each day is a single variable holding one number, it's literally impossible for 2 people to be on call the same day. We never have to write that rule, the shape of our model just guarantees it. That's a classic solver move. Encode the constraints into the structure so you don't have to state them. Now we just talk to the solver. Every rule is one short English sentence turned into a line of code. So first, each day has to be covered by someone who's actually available this week. We use SAD to hand the solver a rule. Or means at least one of these has to be true. So for each day, the person on call is Alice or Bob or whoever's available in the list. Simple. Second rule, nobody works 2 days in a row. So each day must be different person from the day before it. Just read that one out loud. On call today is not equal to on call tomorrow. That's exactly what the code says. No backtracking, no flags, just the facts. Third, keep it fair. Nobody should be hammered and no one should skate by doing nothing. so I count each person's shift. This little if is the trick here. For every day, if this engineer is on call, count as 1, otherwise it's a 0, and the sum adds them all up. Then I tell the solver that the total has to be at least 1 and no more than the max shifts. We pass that in and we'll lean on that number a little bit more later. And finally, the human stuff. The request that makes scheduling painful in real life. Alice can't do Wednesdays. Dan won't do weekends. Bob asks for Friday off. Each one is, again, just a not equal line. And that's the entire problem described. We haven't written a search, a loop over candidates, nothing. We've only stated what's true. And now, let's let Z3 do the work. S-check is that moment of truth. It runs the solver. If the answer is SAT, we ask for the model. That's the solver's actual solution, the specific number it chose for each day. We pull those out as plain Python ints and hand them back. If there's no solution, we return a none. Now let's call it with the full team and say nobody wants to do more than 2 shifts, and we'll give it a run. And there it is, a complete valid week. Alice, Bob, Carol and Dan all slotted in. If you look down that list, you'll see that no one's on call twice in a row. The load's spread in a 2-2-2-1 kind of configuration. Wednesday isn't Alice, the weekend isn't Dan, Friday isn't Bob. Every single rule that we wrote is satisfied, and we never told it how to figure that out. One honest note here though, this is a valid schedule, not necessarily the prettiest schedule. The solver stops the moment it finds something that works. If you wanted it optimized, say the fairest possible way, we can do that too with Z3, but that's more than likely a video for another day. For now, we asked for valid and we got valid. Now here's where things get really interesting and very useful. Picture this, it's Monday morning, Carol has booked the whole week off, probably some well-deserved vacation. And now it's just Alice, Bob and Dan to cover those 7 days. And we still don't want anyone doing more than 2 shifts. Can we even do that? Take a second, think about it. 3 people, 2 shifts each, that's 6 slots for 7 days. Let's run it and see what happens. UNSAT. No valid rota exists. And this is the part I really want you to sit with. Z3 didn't try a few different combinations and shrugged, it just proved mathematically exhaustively that there is no possible way to satisfy all of those rules at once. 6 shifts can't cover 7 days full stop. No human staring at a spreadsheet, no amount of let me just try harder can give you that kind of certainty. The solver gives you that instantly. That's the answer you can't easily get any other way. Not, I couldn't find one, but one cannot exist. So in real life, what do? Well, you loosen the rules. Okay, with Carol away, someone's going to have to do 3 shifts this week instead of 2, and that's a 1 character change. That max shifts variable moves from 2 to 3, and then we run it again. And now we're back in business. Now we've got a fresh, valid rota for the 3 of them. This is the real workflow, and it's lovely. You describe your rules and the solver becomes a conversation. Is this possible? No. What if I relax this? Yes, here you go. You're negotiating with the problem instead of hand coding every outcome. Our rota is a toy, but this exact technique runs serious software. SMT solvers like Z3 are used to formally verify programs and chip designs, proving code can't hit certain bugs. It's the kind of guarantee tests can't give you. They also power symbolic execution in security, hunting for the precise input that triggers a vulnerability. Compilers use them to check optimizations are safe. Cloud providers use them to check access control policies don't accidentally expose your data. Anywhere there are tangled rules and you need a guaranteed answer, a solver is probably in the mix. But one honest catch, so you know where the rough edges are. The more variables and the more rules you pile on, the bigger the search space, and it can grow very fast. For enormous problems, especially those with lots of loops or huge inputs, a solver can get very slow or run out of memory entirely. People call this state space explosion. So SMT solvers aren't magic pixie dust for every single problem, but for constraint puzzles, verification, and is this even possible questions, they're an absolute superpower, and most developers have never even tried one. So, next time you catch yourself writing yet another tangle of nested loops to satisfy a pile of rules, stop and ask yourself whether you could just describe the rules and let a solver do the searching for you. It's just 1 pip install away. I'm going to put the full code in my GitHub repo, and the link will be in the description below, so you can try this, add your own engineers, your own constraints, and see when it tells you what you've asked for is impossible. Hopefully this was useful, and if it was, please like the video and subscribe.